Hi, welcome to RubyKaigi Takeout 2020. I hope you're enjoying all the content. Today, I will be reflecting on Ruby Reflection for rendering RBIs. My name is Ufuk Kayserilioglu, and I'm a production engineering manager on the Ruby infrastructure team at Shopify. So a quick intro to the concept. When I joined Shopify at the beginning of 2019, the first project that I joined was the adoption of Sorbet on our code base. So for those of you who don't know, Sorbet is a static type checker built by the fine people at Stripe. And on the project that I was on, we were trying to adopt gradual typing using Sorbet on our Rails monolith. As we were working on that adoption, we quickly came to the realization that we had a problem with Rubygems. And the reason why we had a problem was that Sorbet doesn't look into your gem dependencies, so it has no way of knowing what's been exported out of those gems. It only type checks your user code. But that's a problem because the cost of entry for the gradual typing adoption with Sorbet is for all references to constants in your code to resolve. So if you're referring to a constant or a module in your code, then Sorbet needs to know what that constant is. But unfortunately, because it doesn't know the constants coming from gems, it has no visibility into those, so it errors out. Quick example for this, which is a contrived code, but it's totally possible that someone has some code like this in their code base. So if you have a myCLI class that subclasses from Thor and calls the class option method, and if you try to type check this with Sorbet, Sorbet will be thinking, what is Thor? Where did that come from? I don't know any Thor class. And also, who defines class option as a method? And also, what parameters does class option accept? Because without knowing that, how am I supposed to type check if the parameter that was supplied, in this case a symbol, is the correct type or not? So because of that, if you try to type check this file using Sorbet, you will get type errors. The way to solve that, which was a concept developed by the Stripe team as they were working on Sorbet, was the concept of Ruby interface files. So Ruby interface files are actually Ruby files without all the implementation detail. So here, I will show you an example of what Thor.RBI might look like. So it again declares the class Thor, and it declares a Thor class methods module, which has a class option method with 2 parameters, and then the Thor class extends from that. So if you write this RBI file by hand and then give it to Sorbet as you're type checking your CLI Ruby file that I've shown you before, then Sorbet will know what Thor is and where the class option method is coming from and what the parameters are. So it will be able to type check this. So this Ruby interface file is like a C header file almost. So if you write this by hand and supply it to Sorbet, then it will be able to type check the whole thing. But this is super hard to do for all the gems that we have a dependency on, and let alone to keep those maintained. In our core, in our monolith, in our code base, we have a dependency on more than 400 gems, and it would be a nightmare to keep those all updated. So can we automate this? And the answer is yes, you can using Ruby Reflection, so that's what I'll be talking about today. So reflection as a concept is the ability of a program to examine or manipulate the type, properties, methods, or values of an object at runtime. And we actually do that a lot in our Ruby programs. You might not be aware of it, but every time you call define method or every time you call alias method, you're actually doing reflection. So we'll just be using the introspection part of reflection to read what these things are and not change them to get all the information that we want. Before we begin, I want to remind you that in Ruby, everything is actually a constant. So we're used to declaring classes using the class keyword or the module keyword, So here the code on the right on top declares a superclass and then declares a full class that subclasses from super, and then declares a bar module inside the full class. But that's exactly the same code as defining a super constant and then assigning the value class.new to it. Class.new creates a new instance of a class. So it creates a new class. And then by assigning it to the super constant, you give it a name. So that's exactly the same thing as doing class super and end. And similarly, if you give an argument to class new, that argument becomes the superclass. And then there's a similar method. So there's a similar class, which is module. And if you call module.new, that creates a new module. Notice that super and foo are constants defined under object because everything lives under object in Ruby. And bar is a constant that lives under the foo constant. So everything in Ruby is actually a constant that lives either in object or under another constant. So I'll be talking about constants throughout this presentation. So this is what you should understand. So we started with this store.rb. So this is, again, an example of what the actual for code might look like, but I stripped it down to its essentials so that we can look at it. And what we're trying to do is to take this store.rb and just using Ruby reflection and no extra outside input to be able to convert that into the corresponding RBI file. So in order to do that, we need to somehow understand the shape of what's being declared in this Ruby file in the store RB, and to grab the parts of it, to grab the name of the top level class, and then the name of the module that's defined inside it, and like all the methods that are defined there, and all the extends and the includes, and then to generate the RBI file. Okay, let's get started. So first of all, we need a way to grab constant references given their name. And that works by calling what we can first call const defined with a question mark and then give it a name. And then that tells us if that constant is defined or not in the given context. In this case, the context is object. And then if we say ask object, is this constant defined, and give it Thor, then it says yes, that constant is defined. Oh, okay, now that we know it's defined, we can actually get a reference to that constant. So that's the const get method. And if we call the const get method, we can assign the return result to a local variable. Note this is like lowercase Thor, so it's a local variable, but it holds a reference to the Thor class. So we can get a reference to the Thor class just using its name. Now that we have a reference, we can call Thor.name, and that will give us as a string the name Thor. So we get our first piece of information, the name of the top level class. So we can use that in our RBI generator. Basically, we're trying to piece together strings to generate an output. But we can do even one better. We can say Thor.superclass, and that gives us object. So now this might be surprising because we didn't declare any superclass for Thor class. But in Ruby, basically, if you don't declare an explicit superclass, the implicit superclass is always object. So that's the piece of information that we get returned. We can also try to get like all the includes and the extends defined in one scope. So we'll try to get those for the Thor class. So all we have to do is to say Thor.included modules. In this case, that returns an empty array because there are no modules that are included in the Thor class. Can we get the list of extends? Yes, we can. All we need to do is to access Thor's singleton class and then ask for the included modules in the singleton class. I won't go into what a singleton class is, but it's basically the class that the Thor class is an instance of. So if we do that, we get Thor class methods. Okay, that's good. But we also get kernel because kernel is included in the singleton class of Thor's superclass, which is object. Object brings in kernel. So we want to get rid of that. and we don't want any outside input into this whole process. So what we can do is we can try to get Thor singleton class included modules, and then subtract from that Thor's superclass singleton class included modules, and which will be kernel. So we would have subtracted kernel, and then we just get Thor class methods. And that gives us the extend that we need. So let's try to grab the subconstants of a constant, all the constants that are defined within the constant that we're looking at. So we can do Thor.constants. That will give us the names of all the constants that are defined inside the Thor class. And in this case, that name, there's only one, and that name is class methods. But that's just the name of it. We want to get access to a reference to that class methods. So what we can do, we know that const get works that way. So if we call const get on Thor and give it that name, so if we do Thor.const get and then give it Thor constants first, then we get a reference to the Thor class methods module, which gives us that module definition there. And we can ask for the name of it to grab the name and to generate it in our RBI. We can also get method names of a constant. So that's also simple. If we do methods and then we call now CM holds a reference to the class methods. And if we call instance methods on CM, that gives us an array of all the instance method names that are defined by class methods. And the fact that I supplied false there means just give me all the methods that are defined by class methods itself. Ignore all the ancestors of class methods. Okay, so we get the name of that method as well. Let's see if we can, again, get an instance of that method too. And well, we actually can, because everything in Ruby is an object. So we can say, we can call cm.instance method and give it the name of the instance method that we want an object for, a reference for. And in this case, we're giving it class option, and that returns an unbound method that represents the class option method in Thor class methods module. Okay, so now we have an object that represents the class option method. Now, can we get the parameters of this method? Sure, we can. If on that method, we call dot parameters, that returns an array of tuples. For each tuple, the first entry is the type of the parameter and the second entry is the name. So in this case, that's saying class option method has two parameters. The first one is a required parameter with the name, and the second parameter is an optional parameter with the name options. An optional parameter means it's got a default value, so you don't have to supply it when calling. A required parameter means it doesn't have a default, so you always have to supply it. So we can also get the parameter names and the different types of parameters if it has a default value or not. We can do even more. We can get the location of a method by calling method.sourceLocation, and that returns, again, a tuple, and the first entry being the file name where that method is defined. The second entry is the line number in that file where the method is defined. So this is useful if you want to check if this method is actually defined in this gem, or that method is defined on this module, but from another gem. So you can actually test to see if it's inside the gem folder or not. And the observant people in the audience will say, wait, you said this is going to be totally automated. You said there wasn't going to be any external inputs into the whole process, but how did we get the initial Thor symbol, right? We supplied the initial Thor name to start this whole chain, but where did that come from? This is a bootstrapping question, and it's a really legitimate question. And the way we found to resolve that was to bootstrap using Sorbet itself. So Sorbet, being a static type checker, needs to understand your Ruby code. Understanding Ruby code means it needs to be able to parse it and make sense of it. So you can actually ask Sorbet to print more than just static type error output. In this case, we're asking Sorbet to print the symbol table of how it sees the symbols in the Thor.rb represented in its own language. And this is like really complex output because it's like very specific to Sorbet. But you can actually see that Sorbet has seen a class named Thor that's being declared in that Ruby file. And it also sees the module Thor class methods. And it actually even sees the method and the arguments to that method, etc. So this actually, we do this to grab all the top level class and module names, and then we use those names to bootstrap this process of reflection to get all the subconstants and to walk down the hierarchy and to generate the RBI. Now you might be asking, yes, but like if you have this ability to find all the classes and the modules in the code base using static analysis, why don't you just do that? Why do you have to do runtime reflection? And the answer to that is because Ruby is a dynamic language. Because Ruby is a dynamic language, there's lots of gems that do a lot of stuff at runtime, right? Creating methods, like creating new classes or new modules at runtime. And if you just use static analysis, you miss those. But if you do runtime reflection, all the code is executed and in memory, so you can actually just walk through that memory contents and all the methods would be defined, all the classes would be defined, and you will have access to a richer representation of the gem. There are a few pitfalls to doing runtime reflection, and I'll just quickly talk about those. So the first is types that lie. So classes or modules that explicitly lie. So in this example, we have a class foo that subclasses from standard error, and it declares two class methods, name and superclass. So what happens is if you call foo.name, what's returned is bar as a string. And if you call foo.superclass, it returns string. But we expect the result of the first thing to be foo as a string, and the result of the second thing to be standard error because that's the superclass, right? So this type is obviously lying. The solution is to call the base method. The base method being the method that actually defines the name and their superclass initially before foo overrode those methods. So the name method is defined by module. And we can get an unbound method that represents that name method like we've seen earlier. So if we ask module, give us the instance method with the name, and it gives us an unbound method. So unbound method, we can't call this unbound method because there's nothing to call it on, but we can bind it to something so that we can call it on that thing. So what we do is we call module.instance method name, and then we bind it to foo, and then we call it, and that will give us the string foo, the real name of the foo class. And similarly, if we get the superclass method on class, and then bind it to foo, and then call it, it gives us the correct superclass standard error. This is made even easier in 2.7 and above versions of Ruby, which introduces a new bind call method. So you don't have to call bind and call separately. So that saves a few keystrokes, but it's also a little bit more performance. So you'd rather use it if you're working with a code base that works on 2.7 and above. Another pitfall you might be running into is this private superclass. So if a class has a superclass, that's a private class, and if we generated an RBI file with that superclass, then Sorbet will say, oh, like, you know, you'd say this is the superclass, but this is a private class, so, you know, I don't know what this is, and it will error out. So we have to be careful with this. So an example situation here is a module mygem that declares a superclass, a class named super, and then says it's a private constant, and then declares a class foo that subclasses from super. So if you say mygem foo.superclass, you get access to like a reference to mygem super. There's nothing wrong with that because that's the superclass. But if you try to access mygem super, then actually you will get a name error because it's a private constant. Mygem is hiding it from the outside world. So the solution for this is actually easy. You check for private. So there's like, you do some evaling. If we define this public module question mark method that accepts a class, we can eval that class, which if the class is referring to a private constant, will raise a name error. And if we catch the name error, we can return false, knowing that it's a private module. And then if we call that method, and if it's false, then we just skip generating that superclass for the class foo. Another pitfall, and this is like one of my favorites, and this is adapted from an actual gem code, but like simplified. So there is a few gems out there that actually use this technique. So this is a class that ends up being its own class. So here it's very simple. You define the class foo and subclass it from standard error, but then you create a new class using class.new that subclasses from foo, but then you assign the result of that to the foo constant by overwriting that name. So what happens is, if you ask foo, what is your superclass? It says my superclass is foo. But you say that's not possible. This class cannot have itself as its superclass. So you check the object IDs. Well, they're different, obviously, because they're different instances. They're just names happen to be the same, and they're not even equal to each other. So the solution here is their names are different. Their names are the same. So they both have the name foo. So if you compare the names and if they're the same, then you can again skip generating that superclass. There's a worse version of this, which I call insidious class hierarchies. So in this case, if you define a class bar and define a class foo that subclasses from bar, and then you overwrite bar by aliasing it to foo, here foo's superclass becomes bar. Foo's superclass's name is the string bar, all fine. But if you ask bar, who are you? It says I'm foo. And if you ask bar, what's your name? It says my name is the foo string. And even worse, in this case, the name trick doesn't work because the name of the foo class and the name of foo's superclass are actually the same, are actually different, sorry. So we can't even skip it. So the solution is to get a fresh reference to the objects from their names. So we get a fresh reference to foo using foo's name and using const get, and we get a fresh reference to foo's superclass using its name and using const get. And in this case, the names will be the same because the bar name refers to foo, and the name of that will be foo as well. So this is the solution. And as for a bonus content, working on our code base, I realized that if you, our code base has a dependency on parser and Rubocop and the OJ gem. And if you require Rubocop first and OJ second, everything works fine. But if you required OJ first and then Rubocop second, you got a name error with an uninitialized constant. Ultimately, I dug this down into a bug in OJ. And what OJ was trying to do was it was trying to remove the constant, basically delete the constant JSON parser, but it was calling remove const on the top level object. So it was actually removing the top level parser constant by mistake. So this was a one-line change that resolved that error in the OJ gem, but it's surprising what things you can discover as you're working with this runtime reflection thing. So in summary, Ruby has a very nice object-oriented reflection API, but the dynamic nature of Ruby makes reflection hard. You need to resort to lots of tricks to get it right. But the nice news is generating Ruby interface files for random gems is now a solved problem because we open sourced the result of all our work as the tapioca gem. So you can go to this GitHub repo, take a look at the code base, and if you're working with Sorbet, you can start using it in your code base as well. Thank you. You can always reach me if you have questions or comments on Twitter or GitHub using the Paracycle handle. It was a pleasure speaking at RubyKaigi Takeout 2020. See you around.